Okay, folks, we'll go ahead and get started. Let me go ahead and open us up in prayer, and I'll give you a sense of the things that we're going to be covering today. So, dear Heavenly Father, Lord, I pray that you would be working in the lives of each of the students in this course. I pray that the material will be clear. Pray that it's just going to contribute to them becoming successful in their future, and also that it will be an enjoyable experience that we get a chance to spend together. Pray that you would help them in their spiritual formation, Lord, that you would help them to really cherish the time that they've been able to study scripture, that they have been able to have a good time to understand how to apply theological ideas and concepts towards their life and give them interesting and creative ways for faith integration. In Jesus' precious name we pray. Amen. Okay, well, we're going to continue like we've been doing up to this point, and I've tried to introduce a couple of things, not only going through some lecture material, but also by encouraging more dialogue that we have in class. And so a lot of that's going to be around our project work. And so now we're slowly working our way through these engineering fundamentals, the way that the author of our textbook has envisioned those. And so what we're going to be talking about for our lecture portion will be the electrical current and related variables. And there are some folks that are engineering. I think I've heard mechanical engineering more than anything else. But there is aspects of electrical concepts that relate to computer science as well as engineering, and I'll try to be pointing that out, and also have a video that I think might make it a little bit more interesting to get some perspective on what we're talking about here. So once again, we're talking about the cyber physical world, the way that we're relating things in this course. And so the cyber is more of the computer science and the physical is more the engineering, but they meet in the middle when we talk about making things real and things that people are going to be able to use and value. And so what we're going to be talking about is electric current, voltage, and electric power. So for some, that may seem like some abstract content here, but you think of like you plug things into the wall, there's 110 volts, roughly speaking, and so that's something that people are familiar with. The idea that you see how much current is being drawn from when you plug something in, and this idea of electric power, I think we'll have some idea of our day-to-day experience that those are things that we're familiar with. And so it gives us a chance to describe the role of current as a fundamental dimension in engineering analysis, explain the basic principles of electricity, electrical currents and components. What we want to be thinking about is these elements here. And so the most basic elements, maybe the engineers would know about resistors, capacitors, stuff like that, and inductors. But when you think of like integrated circuits, microelectronics, that's probably something that more of you have a better sense of understanding what it is, a central processing unit and things like that. Electrical power sources, thinking in terms of batteries or thinking of solar panels. Anybody seen solar panels? Or around my town where I live, it's becoming more and more popular. And then electric motors, and I'm going to describe the role of motors in our everyday life and give examples. And actually, I'm going to include a video. It's not by Tesla or Elon Musk, but it's about his Tesla vehicles. And so that might be interesting to give you a perspective and introduce you to a practical application of electric motors. And finally, lighting systems, explain lighting terminology and give examples of the different lighting system and their power consumption rates. Maybe you've ever noticed probably now it's getting to be a little bit older, but incandescent light bulbs, you guys have probably had those in your home. Now you're probably either using neon or LED lights, like these are neon lights. And what happens is actually the illumination is slightly color tinted in one direction or another. Incandescent lights was a little bit more rich in the yellow and reddish tones and stuff like that. These tend to be a little bit more, I think it's more of a greenish, bluish type of tint. And so if you were to take a picture with your neon light versus if you're an incandescent light, it would be different. And then with LED lights, you actually can get different, some you can actually program, you can get the kind of coloration that you want. And so this gets into something that they're talking about for lighting systems from another dimension that we haven't talked about yet. So in terms of electric current, voltage, and electric power, so we have already talked about this. Electric current as a fundamental dimension. It's kind of a complicated way that they address a unit of current, but the SI units is Coulomb. The unit of charge is the Coulomb. That's like how much is in, like, say, some type of, well, a capacitor is, have electrical engineering background, and so that's when I think of a Coulomb, that relates to the amount of electrical charge that's in some type of a source like a capacitor. How many know what I'm talking about when I say capacitor? Just give me a show of hands. Okay, so that's kind of a new concept. Maybe I'll just give an example. And so you can be thinking of like two large plates. And so what you're doing is you're trying to get plus accumulation or lack of accumulation on one or the other side. And so when you get this kind of a situation, it causes an attraction. And so it's going to keep these positive charges on this side and these negative charges on the other side. And so the amount of charge is how we calculate that, as something called the Coulomb. And so just to maybe give you a little bit of a perspective of what I mean when I say that. So voltage represents the amount of work required to move a charge between 2 points. There's the equation, the way they have it written, I'm used to seeing it a slightly different way, but I'll get to that in a minute to give you a perspective. And so like AC, alternating current voltage, like we plug into the wall, it's like that. If I plug into like my computer, this is DC. It's just done this AC to DC conversion for a certain voltage range that is spec for what this computer needs. And so like if I have like this charger, this is going into a USB-C connection, that is actually specifies a certain amount of voltage is done there. But if I had looking around the room, some different types of computers, if you have it plugged in, it may or may not be the same voltage. And so thus we can see different kinds of voltages that are used for one application or another. So direct current, the flow of the electric charge that occurs in one direction. Directed current is typically produced by batteries and direct current generators. Alternating current is a flow of electric charge that periodically reverses, and so goes positive and negative. The time interval between the peak value of the current on 2 successive cycles is called the period. And so does anyone know what the period is for AC electricity here in the United States? It's 60 hertz. Anybody have an idea or a guess what it might be in Europe? They actually use 50 hertz. And so it just gives you an example of some of those numbers. And for this audience, it's okay that those are some things that aren't known. I'm just going to skip over this. So basically it's just showing the conservation of current. And so if you go to, that's what's just trying to be showing you here. You go in an intersection and I1 may not be equal to I3 and I2 might not be equal to I4, but these combinations would be the same. So that's just a little bit of information about that. In terms of electrical circuits and components. So here are examples of some electrical components, some of that you might be familiar with. I think everybody's familiar with wires, at least you've seen them. Maybe you haven't actually used them other than the fact that they're in the background in your home or your computer or something. Switch, so you can turn things on and off. You know, when I come in here in the room, I turn the light switch on. The outlets is where you can plug devices in. I plugged my laptop into one. And then I mentioned resistors and capacitors. Those are common things. There's also something called the inductor, but it's just another component that has another set of characteristics on how it would handle current. So resistors, it resists that. It's like when you have like you turn the water faucet on and you turn it on higher and higher, you're having less resistance, so more water is flowing. That's the same kind of thing that's happening for a resistor. The higher resistance, the more it's preventing the current flow, so it's going to go slower. It's like turning the faucet off. Capacitor stores charge. So I tried to give an illustration of what that might look like here. So what was that? Just trying to show you two plates, and it doesn't necessarily allow current to flow, but it stores it up. When you have alternating current, what that does is it's trying to go one way, and then it's going to store up on one side, and it's going to go the other side, and it's going to store it up in the other. So it's actually going to have some interesting characteristics in terms of what it's going to do overall. So I already gave you an idea of thinking about resistance. And so just think of it resists. That's the key part of this, is resisting what is allowed in terms of the electrical current. And the general relationship for this is, I'm used to having it V equals IR, but if V equals RI, R stands for resistance, I stands for current, V stands for voltage. And so that's the relationship between those ideas. There's something called the wire gauge. And so you maybe like an 18 or 24 gauge, really small, getting to larger wires. And so this is just the system in which they specify different things. So like if you had like some home improvements, what the contractors would have to go and use different gauge wires for different things. And so if it's requires a lot more current to go through it, that wire is supposed to be bigger so it doesn't overheat. It has the real estate, if you will, to be able to handle that. There's also electric power, and the relationship between that is power is equal to voltage times the current, VI. And so that's another thing that's out there in terms of a relationship. So basically, this is something that we all use, going from our cell phone to our appliances. And this is now that my wife and I have a solar and battery system in our home, a solar power system. Kilowatt hours is another way of talking about power. It's power per amount of time. And so it's energy. And so it's just telling about how much energy is utilized for any particular time. So it's talking about the annual electrical consumption is somewhere between 4,000 and 10,000 kilowatt hours for a typical home in a year. And so that can give you, if you break that down, how much what it would be on average for a day. So there's two general concepts of the ways that circuits can be put together. You can either put them in serial versus you can put them in parallel. I won't dwell on this too much because most of you guys aren't familiar with it. So I'll just show you an example for resistors. If I did this and then have another one, that's called in series. And guess what? If you're trying to pass something along this wire, you have these things too in series. What do you think? Is that going to cause more resistance versus if I just had one? So that's one situation. But if I had two resistors in parallel, this may not be as intuitive, but there's a relationship between this, that the the total resistance is equal to the resistance of one plus the resistance of the other. This is a little bit hard to write like this. So we just, so anyway, just, I believe that's what the equation is. So, if you solve this, so you came up with a total R, you can see that this is actually less than it would be for either one of these resistors. Capacitors, they store charge. The farad is a unit that's used for that. So this just gives you another example. For the folks that are computer science, you probably aren't going to bump into this, but I'm just trying to give you a sense of the types of units and things that we have in this chapter. So what I showed you, the difference between series and parallel here. This is for resistors. It's actually goes, it's the opposite if I was to show you that for capacitors, but I'm not going to get into too much detail. So maybe just thinking about it, put it up as a higher level. And so if I was to try and think of things in our home, so let's say, for example, I have a refrigerator, I have an air conditioner, and any other device you want to say that I would include for giving you a sense of what I'm trying to talk about here? What's a common device that you use that you might want me to put down here? Anybody want to give me an idea? TV? Okay. So what happens when you go to the power company, what it is all of these things are in parallel. So that means that the total resistance is less with these three things being in parallel. So it means it's going to draw more current. That's the idea, giving you a sense of what's going on. So thus, we can see the impact of putting things in parallel. If I put them in series, what's going to happen is these things aren't going to work because each one needs a certain amount of voltage for them to work. And so it's going to get smaller and smaller and smaller. And so if I think like a home application, that's not going to work. But if I have the ability to get more current to come through this, and the power company has it available, then this is an example of something that would work. Does that make sense? So just wanted to keep things at a higher level to be exploring that. So what about electric power sources? First of all, batteries. I see a couple of you guys, maybe most of you guys are on battery power with your laptop. So the batteries is using a chemical reaction to produce the energy that you're using for your computer. And so guess what? Over time, it's only good for so many hours. And then it's going to say, oh, sorry, it's going to just shut down your machine, or it's going to give you a warning a little bit before that says you need to recharge. So the circuits create paths for the electrons to flow. Okay. And so it's trying to mimic, at least for a laptop, when you have it, when you're plugged in, the same as when you have it going on battery. When it's turned off, there's no path. And so there shouldn't be any reduction in the power for the battery. But since it is a chemical reaction, they will start to discharge a little bit over time. If you've ever had like a laptop in your closet for a while and you pull it out and you haven't used it for a while, it's still going to lose some of its charge. So it's chemical compounds. All of those are the things that are part of a battery. Photo emissions. So just think of your solar panels as an example. So when the light hits the surface, it engages with the solar panels and it starts to produce a current. And this is something that can be used to operate a home. Like that's what we have. And so during the day, we get good solar production. Then as it gets towards the evening, it starts to go down and eventually you run out. And so you can either have to use things from the power company or what we have is we have a battery and a solar panel combination that we could literally go, if we wanted to, we could go off the grid. There's other forms of energy, wind energy, turbines. It's common in different parts of Europe where they have steady trade winds. And so they just take advantage of that. Different places in the United States, they'll have like wind farms that are utilized. For folks that are near a river or a dam like Hansen Dam or something like that, and there's overflow, they're trying to maintain the level of water, so they do let some water through, and so that they can actually generate electricity by having that water pass through turbines. Those turbines are connected to a device that produces power from that. And plus there's power plants. So water is used in steam power generators to produce the electricity. So they warm up the water that goes through these turbines and it produces electricity. Finally, nuclear energy. There was a power plant between San Diego and Orange County, and they just recently have started the process of decommissioning it. It can actually take a long time to decommission it. So the San Onofre plant, if you've ever seen that, in front of Camp Pendleton. So those are a couple of different kinds of different types of energy that are available. Wind energy is a form of what? Anybody have an idea? Yeah. So you're turning a turbine and it's generating electricity. Okay, electric motors. So motors drive many devices and equipments that make our lives comfortable and less laborious. Some household appliances and motors are refrigerators, garage disposals, microwaves, I mentioned TVs. So microwaves with a turntable, stove hood with a fan, it goes on and on and on. And so there's different types of motor types. Selecting a motor for an application depends on several factors, including the speed of the motor, the power required, and the type of load. The duty cycle, manufacturers of motors classify them according to the amount of time for motor needs to be operated. The motors are generally classified as continuous duty or intermittent duty. So let's play this video and then we'll have a discussion about it and see if you have any observations from what you saw. So this is about the Tesla cars. Anybody seen a Tesla car running around as you drive? They're quite common here in California. And so go ahead and play this.
This is Nikola Tesla, the greatest inventor of all time, and this is his greatest invention, the AC induction motor. In the early 21st century, modern inventors like Elon Musk started putting these AC induction motors into electric cars. From this, Tesla Motors was born. Elon Musk's Tesla has been constantly improving on that century-old design, from their Model S to the Model 3 and on to their next generation electric car that has yet to even be released. This is how Tesla reinvented the electric motor. The AC induction motor is a product that goes back to the early days of Tesla Motors and the development of their first roadster vehicle. But in the grand scheme of things, the induction motor actually tracks its origin back to the early days of the Industrial Revolution. Alternating current is the kind of electricity that surrounds us on a daily basis. It's what comes out of the sockets in your wall and moves through the power lines up and down your street. Nikola Tesla is widely considered to be the father of alternating current electricity and was a pivotal figure in adopting AC to power the US electrical grid around the turn of the 20th century. Many people consider Tesla's greatest invention to be the alternating current induction motor, essentially a device that will transform AC electricity into mechanical motion, and in turn, when used in the opposite direction, an induction motor can turn motion into electricity. One of the first large-scale applications of Tesla's AC generator was capturing hydroelectricity at Niagara Falls. When we say alternating current, we are really talking about the direction that electricity is moving through a circuit. So for AC electricity to work, the direction of the electric current has to continuously alternate between forwards and backwards. This is a bit difficult to imagine in the context of our own electrical grid. As far as we can tell, electricity flows out of the generating station and into our house, but in reality, it's in a constant state of movement back and forth. This is a characteristic that allows AC electricity to be transmitted at high voltages over very long distances and then converted into lower voltage for final delivery to the consumer. The alternating flow happens so fast that we only perceive the electricity as constant, but in reality, the direction of electricity alternates 60 times per second in North America. So how does this apply to electric motors? Well, it's all about magnets. So when you transmit electricity through a conductive material like a copper wire, you also create a magnetic field in that wire. This is an electromagnet, and once you stop the flow of electricity, the magnetic field will also dissipate. Now, if you transfer electricity in one direction through a conductor, you create a magnetic pole, either a south pole or a north pole. And then if you were to reverse the flow of electricity through that same conductor, you would also reverse the polarity of the magnetic field. So as the direction of electricity alternates, so does the north and south pole of the electromagnet. There are two essential components of an electric motor, the stator and the rotor. The rotor rotates and the stator remains stationary. Easy way to remember which is which. Now, as the name suggests, an induction motor uses a rotating magnetic field in the stator to induce a rotational force in the rotor. Here is how that breaks down. Your stator is essentially a ring of copper wire that is arranged into coils that run from the front to the back of the motor. Each coil of wire is wrapped around a piece of iron, so when electricity is flowed through the coil of wire, it becomes a powerful electromagnet. The polarity of each magnet is determined by the direction of current. So by alternating the directions of the electrical charge being applied to each subsequent winding and flipping each polarity in sequence, we create a rotating magnetic field that travels around the ring of the stator. The speed at which the magnetic field rotates can then be controlled by the rate at which you can alternate the flow of electricity. The rotor in this case is a much more simple component. There are various different kinds of rotors used in different induction motor designs, but the one that we are going to focus on today is known as the squirrel cage rotor. It gets the name because the structure is a cylinder made from aluminum bars that run from the front to the back of the rotor with circular metal end caps. There is no supply of electricity flowing into the rotor, and it contains no natural magnets. It's literally just a metal cage that can freely rotate, and yet the rotor can be transformed into a magnet by the rotating magnetic field of the stator. One of the interesting things about magnets is that they move relative to a conductive material. They can induce an electrical current into that conductor, which in turn creates an electromagnet with no contact required, just relative motion. You can see this by dropping a magnet straight down a copper pipe. As the magnet falls, it will induce a magnetic field into the pipe, which will then work against the magnet itself and slow the fall of the magnet through the tube. So the further it falls, the slower it will move through the air due to resistance from the induced magnetic field in the copper pipe. The same thing is happening inside the induction motor. By rotating the magnetic field around the stator using alternating current and electromagnets, a magnetic field will be induced in the bars of the squirrel cage rotor. That induced magnetic field will react against the magnetism of the stator. We know that magnets with the same polarity will push against each other, and this force of magnetism will cause the rotor to turn in the direction of the stator's magnetic field. So the faster you alternate the flow of current through the stator, the faster the rotation of the magnetic field, and the faster the movement of the rotor due to the magnetic push effect. The only caveat we need to remember is that the rotor will have to move at a slower rate than the rotating field of the stator, because the magnetic field is created by relative motion. If the two are turning in sync, then there's no longer any of that motion in play. The rotor will demagnetize and slow down. From the time this induction motor was first patented by Nikola Tesla, 1888, to the present day, AC motors have been a staple of industrial society. We see them in everything from elevators and streetcars to ceiling fans and washing machines. Anything that plugs into the electrical grid and spins is more than likely to have an AC induction motor inside. So when it came time for Elon Musk and his crew of founders at Tesla Motors to choose a power source for their first electric roadster vehicle, there was one very obvious candidate, the AC induction motor. And when used in an electric vehicle, the design gives you one significant advantage. We know that when you rotate the magnets of the stator faster than the rotor, you electrify the rotor and create a magnet. But when you spin the rotor faster than the stator using an external force like a wheel, you electrify the stator, which can then transfer the excess energy back to the battery pack and increase the driving range of your vehicle. This is how regenerative braking works. Tesla retained the AC induction motor as their primary drive unit into the Model S and X. This allowed the relatively large and heavy vehicles to achieve mind-boggling feats of acceleration from a standing start, but they also came with a significant drawback that needed to be solved. So the beauty of the AC induction motor is its simplicity. Coils of copper wire, some chunks of steel and iron, a squirrel cage of aluminum bars, not much to it. And that's exactly why the motors in appliances like air conditioners and washing machines can run for decades without failure. The downsides of the original induction motor start to show themselves only when you go in search of maximum power and efficiency, which is exactly what Tesla was looking for when they designed their Model 3. Okay, so everything that we just talked about still applies to this new motor that Tesla created for their Model 3, but with one key addition: permanent magnets. Specifically, they added permanent magnets to the rotor. So now, instead of an aluminum squirrel cage, we have this dense iron core filled with strips of a magnetic rare earth element called neodymium. The technical name for this new motor type is IPM SYN-RM. That means internal permanent magnet synchronous reluctance motor. It's complicated. Here's the scoop. You could make a permanent magnet motor by taking a metal cylinder, sticking 4 magnets to the outside with south poles on the top and bottom and north poles on the sides. That would be your rotor. And then when you stick that inside the stator that we talked about before and start rotating the electromagnetic field in the stator coils, your permanent magnet rotor will follow. Now we can actually spin the rotor at the exact same speed as the rotating magnetic field of the stator, because we are no longer relying on relative motion to induce the magnetism in the rotor. This already gives us higher efficiency and more power, particularly when accelerating from a stop, because we have these two very powerful magnetic fields that can instantly push off from each other. But there's a big problem. 2 problems, really. For one, permanent magnets stuck to the outside of the rotor will have a tendency to come unstuck due to centrifugal force, so the faster the rotor spins, the more likely it is to fly apart. But even more importantly, reason 2, is that the rotation of the permanent magnets will start to induce their own magnetic field into the stator coils at high speed, and this is going to be opposite to the electromagnetic flow in the stator, and that force is going to want to slow down the whole system. This is called back EMF, and the faster the rotor speed, the more back EMF you get. To combat these 2 downsides, we introduced the design of a reluctance motor. So aluminum and copper are only magnetic when you flow electricity through them, but iron is naturally attracted to magnetic fields. So that means we can use it as a rotor material inside our same old electromagnet stator, and that iron rotor will follow in sync with the rotation of the stator's magnetic field. Again, there is one caveat. We need to cut channels into the iron material that line up with the shape of the magnetic field that surrounds it. This will align the magnetic reluctance of the iron core with the magnetic field of the stator and allow them to rotate in sync. This is our synchronous reluctance motor. It's a very efficient motor design, and it works very well at high speed because there is no back EMF created by the iron rotor. The downside here is that a reluctance motor has very low power density when accelerating at low speed because the rotor can only follow the rotating magnetic field of the stator. You don't get that instant push effect of 2 magnetic fields working against each other. Now, all we need to do is add magnets to the rotor and we get our perfect combination. Those channels that we cut into the iron core make the ideal location for our permanent magnets to live. This is our internal permanent magnet. By placing them inside the iron rotor, we reduce the permanent magnet's effect on the stator windings and thereby reduce the problem of back EMF. Now, there is still a very complex task here that involves balancing the reluctance effect of the iron core with the magnetic push of the permanent magnets. You see, you want to utilize the power of permanent magnets during acceleration, but then cancel them out and switch over the efficiency of reluctance at cruising speed. This is all handled by very advanced software controlling the magnetic field of the stator that we cannot even begin to explain. And this is why the IBM SIN-RM motor was never widely used until Tesla came along. And now Tesla is about to take this design to the next level. With the motor design for the Model 3, Tesla was able to maximize both power and efficiency, but it did come at a cost. If we remember back to the original induction motor, it came with a relatively simple and cheap rotor made of aluminum bars. By switching to IBM SIN-RM, Tesla introduced the rare earth element neodymium into their rotor. So the cost in this instance is money. It's a much more expensive motor. Now Tesla is dedicating their research and development into a next generation vehicle platform that is supposed to dramatically reduce cost while maximizing efficiency. This will serve as the base for their upcoming robotaxi vehicle. From what we learned last year at Tesla's Investor Day, the designers are achieving much of that cost reduction by eliminating rare earth elements from the motor's composition. Now, it's not that neodymium is particularly scarce in the overall composition of the Earth, but it is difficult to locate near the surface, and you typically won't find large concentrations all in one place, so therefore the cost is relatively high, and the supply is relatively low. But engineers still prefer neodymium for electric motors because it has a strong magnetic field that won't degrade over long periods of use. So it does justify the cost. Now, Tesla is saying that they can get by without the need for any rare earth elements in their new magnets. So what will they use instead? A widely popular material for making magnets is called ferrite. This is a ceramic material of mostly iron oxide, also known as rust, combined with additional metals like manganese, nickel, and zinc, but it doesn't particularly matter which one. You'd find ceramic ferrite magnets in everything from speakers to electric guitars and cordless drills. They also help keep your refrigerator door closed, so it's a very common and affordable material. The downside of ferrite compared to neodymium is magnetic strength. You would need a much larger quantity of ferrite to match the strength of a neodymium magnet, and there's not much extra space to go around inside an electric motor. We know that Tesla can make some of this back by increasing efficiency. They've done that in the past. Just in the time between Model 3 and Model Y, the engineers were able to reduce the amount of rare earth material required for the electric motor without sacrificing any power. But inevitably, by switching over to a ferrite magnet, Tesla will lose some performance in their next-gen vehicle. So now, instead of going 0 to 60 in 6 seconds, it might take 8 or 9 seconds. Is that the end of the world? Absolutely not. This is a vehicle made for mass transportation, not the racetrack. Going all the way back to Nikola Tesla, good inventors are simply trying to extract more functionality from the world around them. How can we do more work with less energy? How do we combine different principles to create something new and more effective? And that is what Tesla, the company, has continued to do throughout the past 2
Okay, well, I hope that was interesting. Maybe the engineers or the nerds will really love that. Others might, maybe not so much, but anyway, why don't we just think about that? So, how many people found that useful? How many people not so much? Okay, so a little bit of a mixed reaction, but mostly interesting. Some of you might like what Elon Musk is doing, he's an entrepreneur. And so just leaving it at that is interesting to see what he's doing, trying to make a better world. And he's been doing interesting things with technology, and I'll just leave it at that for the purpose of our conversation. So there's just one more topic that I mentioned a little bit earlier, and that's in terms of lighting systems. lighting your home, lighting a business of operation, a school. All of these are places where illumination is something that needs to be thought about. And so if you had lower power illumination that had the same amount of light that was being generated, that would be a good thing. And a common unit of illumination intensity is something called foot candle. But that's just something that I won't get into too much detail other than to say that there are units that are standardized that are out there that we use. But there was also this color rendition index, the CRI that I was mentioning. So I mentioned incandescent light bulbs. And so it's kind of like having a campfire, if you will, that has some of that richness or the sun. And so you can get a little bit of, might actually make your complexion look a little bit nicer when you're taking pictures of versus other types of illumination. If you had it with neon lights, you might look a little bit more greenish or something. And so those are just things that can be thought about. But these are things that can be corrected. And so either with your camera or you can correct the light source so it has a more even spectrum. And those are the kind of things that are available to help with this color rendition index. Any comments or questions on what we covered? That's just a quick synopsis of this chapter as we're thinking a little bit about electricity and its various elements that come into play. Okay, well, let me finish up with this one and talk more about our project-related work. I've started to introduce another source of material that I think is useful for us to have as part of our discussion. I will remind people that what I'm trying to do on Tuesdays to be more of a time for conversation. So I am keeping record of who is in class so that we can credit that appropriately, because I want to have that dialogue and have us be able to create a sense of community of our time together. So let me just go ahead and review a little bit of information of what we've covered from this other source. The way that I'll do it is I'll go back to the beginning here and just talk about it this way. So the way that this textbook applies, getting us an overview of engineering and computing, is it talks about what engineers do, elements of engineering analysis, some fundamental elements, force and motion, energy and economics. So we've had some things to talk about that in the way our textbook is oriented. Then they have chapters on specific parts of engineering and computers. And so if it turns out that any one of you are interested in one particular area, this can be one of the things that we can spend a little bit more time on. I wasn't planning to do that. And then last time I did chapter 19, where we did an introduction to engineering design. And so what I'm going to focus on today is to be focusing on design teams and why that's important. Anybody have an idea? Or what are some of your thoughts on why would having a design team be a useful thing to have? Anybody have an idea? Share ideas. Yeah, share ideas. Any other thoughts why having a design team would be helpful? Delegating tasks. So sharing ideas, delegating tasks. Does anyone find they're an expert on everything? So why do you think a team, what were some other reasons why a team would be a useful thing to have? Go ahead. Yeah. Right. Yeah. True. Very, very good point. Yes?
It takes less time to complete tasks than it would for a single person to complete those.
Yeah. Everything that you've mentioned, and I mentioned there's a half a dozen other things that people haven't said as of yet, are extremely good points. And those are exactly the reason why having a team is useful. And so you code as a team, you engineer as a team, And so all of those are things that are vitally important. So I wanted to go over this next chapter to be thinking about that aspect of what it would mean. Maybe another area is having project management. You have to be thinking, if somebody is paying you to do something, they're going to want to know, when is it going to be done? How much is it going to cost? How much resources is it going to take? All of those are the kind of things that they happen. And so this term that comes along with this is failure to plan is planning to fail. And so each of you will have to do a senior capstone project. And this is going to touch in some of the work that you'll be doing in that, is that you need to be planning and having those things available so other people can think about that. So here are 4 important project management topics. So the teamwork, we talked about that. It's going to be more efficient. There's going to be more ideas. Documentation, not a real fun thing in some way, but if you actually document as you go, we'll be talking about how that's going to be making that better. Scheduling. And so what managers want to know is, are you on schedule? Are you on task? Or are there any issues that need to be worked out? Those are going to be things that would be captured. And finally, time management. So can you make it a little bit more efficient? Is everybody getting the things that they need? Those are some things that start to come up. Well, here's another part of why it is useful to work as a team. I've never worked on some kind of firearms, but back in the 1800s, a musket had 51 parts. Just give you a perspective. A rifle later on in the 1840s had 140. A bicycle has greater than 200 parts. That's as the late 1800s. An automobile has over 10,000 parts. And then you think of an airplane, the Boeing 747, has more than 5 million parts. And so no one person is going to have the expertise for all of that. So it's definitely something that we want to be mindful of and to be working together as a team. Here's another dimension. All of these things need to be working together. That's the only way you're actually going to get success: ability, effort, and attitude. So maybe you have 1 or 2 of those things, but you need all 3 of those working together. And so that can be a challenge. And so the team dynamics is something that you want to be looking at. So that's one of the things that I'm trying to do with our work here, is having us work together as a community, as a team. We're working on some project works. Even though we're doing it individually, I'm trying to encourage people to comment on what other people are doing, maybe make some suggestions or recommendations. All of that is something that would be beneficial for us to successfully do our projects. So for a team, you need to have a common goal. So maybe as a team, or at least my goal for us is to have everybody do well in this class, to have an enjoyable, successful experience. You need to have leadership. Someone needs to be the one that, oftentimes you need to have a person that's speaking for the whole group. That's something where that comes out. Each member makes a unique contribution. So who does what? You want to have effective team communication. I'm trying to promote good communication, having you guys give me feedback, and also try and be engaged with your projects that you're doing. Creative spark. I think as a result of some of our conversations, we've had a little bit more illumination for projects and clarification, and hopefully making it more interesting for you. Harmonious team member relationships. It's important to have good relationships with your peers. And finally, have effective planning and resource use. Make sense? So successful team member attributes is attendance. Everybody needs to be there and involved. And so that's why I'm encouraging that we spend time together. Being responsible. So you say you're going to do something, you're going to commit to doing that. Abilities. Being clear about, hey, I have experience. I've used this software before. I've done coding in this. I'm familiar with the mechanical engineering aspects of this. I know how to be thinking about the electrical parts. I know how to do some modeling and simulation, stuff like that. Being creative and energetic. I always like to say brainstorming is a good thing. And I like to say that the laws of physics temporarily don't apply when you're doing brainstorming. Just get those ideas out there and start to figure out what is in the realm of possible. And personality, trying to be accommodating and working with each individual in the team. So what are the three types of documentation? So a design logbook. So maybe in engineering, this is a little bit easier to get your head around it, and you have a notebook and you write everything in that notebook. You don't erase things. You just keep a record, a running record of what works, what doesn't work. You need to have communication with management, and you need to have communication about the final design. These are just examples of the kind of things that are there. So maybe it's a blueprint, maybe it's the source code, maybe it's a prototype. It could be any number of things that you're leveraging. Many types of information should be documented. And so you can have things you're documenting versus an email, having CAD drawings, things that are in your lab notebook as you start to figure out, well, what is the basis for how you're going to be putting this together? It could be some modeling. You could have some universal modeling language. It could be something for your hardware or for your software. These are just a variety of examples of the types of things that you would want to have for documentation. In terms of the logbook, I mentioned this a little bit, having something that's bound, that's a bound notebook. So it's always together. So having a 3 ring binder, you don't want to erase areas, you want to cross them out. So you might have to go back to that. You want to keep record of everything that you've done. He wants to make sure it's legible to not only you, but others. You don't want to use loose paper, glue or staple in supplementary information. Maybe you have a printout from a piece of test equipment. You put that into your lab notebook and put your name and contact information on the cover. So it may be yours now, but as you're moving on to another project, they would say, be keeping that information. So the next person would have that available, they could refer to. What should be documented in your logbook? The answer is all the information needed to develop the design. The justification for the design decision, that's also useful. Why are they used? You don't want to lose information. You don't want to reinvent the wheel. So you look back in your notebook or maybe the one previous to that and you says, aha, we've actually did something like this. You can pass on information to others. It could be required to defend a patent. So this is something either if you're opening your own company or you want to make sure because you can get revenue from patents. And plus it protects you in a lawsuit. You have the date and time when you did this and someone's challenging that you're copying their ideas and you show that, well, no, we had this years before you were actually starting to say that you had it. So what should go in the logbook? Basically everything related to the project, meeting notes, calculations, sketches, ideas, everything like that. What not to put in, entering your personal opinions about the design, that's not relevant. For example, say there's a 70% chance a crack will develop instead of saying the design is dangerous. So this first one isn't saying that you're giving an opinion, but you're actually based on some analysis, you're giving a perspective on what is the state of the design. So I'm not going to enforce this discipline for what we're doing, but I'd recommend that you keep all of the information that you're doing in your project. You find some things and maybe you revector what you did for your final what you're going to do in your project. That's stuff that you want to make sure that you keep assembled with what your project work. And so I'll just keep that at that for the context of what we're doing in our class. What about communicating with management? I guess I have to say that maybe in a sense, I'm management in this situation just as a mock-up for the class. So so these are used to review the project details. It can be paper or presentation based. So I'd recommend the what I have for the assignment is you have a write-up for that, and then we can have a chance for everybody to contribute your ideas in class. You want to consider your audience. What do they know? What do they not know? And be prepared. All of those things are beneficial. So what are the ways that you want to communicate the design details? Computer files, design drawings, assembly drawings, bill of materials. If we were actually going to have something to build a print, this is where it starts to get into those kind of things. That's going to be beyond what we're focusing on here. Engineering drawings, you need to have the dimensions, tolerances, materials. We saw that video of what Tesla is doing, and so that they were trying to get away from rare earth elements. That could be an example of over time trying to go from one type of material list to something that's more easily available, but still trying to keep your performance within your goals. That's just another follow-on to that to be thinking about. Any comments or observations on what we've shared about this so far? Just giving you more insight of what does it mean to be working as a team? So I already mentioned this, having a bill of material. This is going to be beyond the focus of what we're going to be doing in our class, so I won't really focus on that. So successful projects meet 4 goals. They're within budget, they meet specification, they're on time, and they have client acceptance. So that's the goal that you're trying to seek with your project work. Plan your time well. This is where it can be deceiving. You really need to put a lot of effort in the beginning. A lot of my career work has been working in system engineering. You're trying to find issues as soon as possible so that if you don't get this thing way at the end where it's really costly to retrofit and you get this kind of a situation, the cost to change over time gets greater and greater. The ability to change becomes less and less. And so those are going against you in both ways, and you want to be preventing that. So examples of project management tools, having a statement of work. That was your proposal. What is it that you're going to be doing? And so having a work breakdown structure, a list of tasks to complete. We didn't have that for this, but if you were actually having this monetized, that would be an example of something that would be required. What are the list of responsibilities that various individuals are doing? That would be something that you would have to capture. Project management tools, you would need to have a PERT, a program review and evaluation technique, which is a graphical review task flow. And so what things lead to what to actually get you to a point of where you're going to finish. Critical path is taking that PERT chart and finding, well, what is the one that is the longest, the thing that's going to stretch out the schedule the most, the thing that you need to make sure that you cover. And so that's what you would have that is part of your project management. And a Gantt chart, and this is another tool, is having a schedule that it shows you what and when they start, when they finish, and what leads to what. And also having something called a percent complete matrix is when you're done, you're 100%. When you start, you're 0. And so what is the percent complete on these various tasks that need to come together for you to have success? So what about something like an engine rebuild? And so you go to your auto mechanic and they say, okay, it's going to be this many hours. It's going to cost this much. And so basically they've done all the hard work. They've done this a number of times. And so this is what they have. But let's say, for example, you're doing it for a first time. Maybe it's a new engine. Maybe you think of the car manufacturer of your choice, Ford or whatever. And these are the kind of things that they would be doing. All of the various steps that would be taken, getting the engine out, assessing at them. Maybe you have to do things to the engine case. If you have pistons, and so you're going to have to rework the pistons and replace them. The rocker arms, all of these are things that have to be laid out. And so you can be seen, this is what they're talking about. It would be taken on the order of 4 weeks to do. So this is if you're doing it on your own, you could probably handle that. If it's you taking it into the auto shop, you probably want it back by tomorrow. And so that may or may not be possible, depending on how long it takes them to get the parts and to work through each of these items of this schedule. So for the schedule, it's using daily and long-term calendars. What do I need to do today? What is the things that are longer term, and what are vital? What are important? What is optional? You need to make sure you do all your level A components. The B would be important. C, you fit them in whenever there's time, and so you want to keep those in balance of what this is. And this can be an example of how you look at your prioritization, what's complete, what's deleted, what's in progress. And so here you're seeing all the 8 items are completed. That's good. Maybe you find some stamps, you don't need to do that. This one's in review, and here you have a C item, and so that's something that you really need to focus on. You'll get to it when you can. So what you should do, so using a planner is a beneficial thing to be utilizing, having daily prioritize things as well as a calendar for longer term events. Well, I'm just going to go back to the contents, go back to the section that's covering what we're talking about for these steps here. We've talked about 2 of the several steps that we have. And I'm just going to now open it up and see if anybody has any comments on questions on this. Let's see if we can try and relate this with the rest of the time that we have to our project work. And we can focus a little bit more on this on Thursday. So we talked about an introduction to the engineering design last time. Now we've got a chance to be thinking in terms of teams. So I'll put up our project list and just open it up for conversation to see if you have any points to make about this. Give me a second. So how's it going? I know a lot of this is thinking, we're getting some things worked out. Some of you are doing some more research and refining the work that you're doing. Anything that you folks want to provide some comments back on where things are at? Who's doing the smart door locks? I'll just kind of pick one arbitrarily here for a discussion. Okay, the folks online have been contributing, so I appreciate that. So we don't, I can look it up, but I won't do it real time here to see if who is doing the smart door locks. Okay, well, maybe that's a good place to call it a day for now. I appreciate your involvement. I really want to see what we can be all doing to make our projects the best that we can. And Hope you have a good rest of your day, okay? Take care.